everyone, welcome to today's lesson. We are on lesson 1-10, and in this lesson what we're going to learn is how to apply an algebraic method for testing whether functions are even, odd, or neither. Our language objective is to explain the steps we use when determining whether a function is even, odd, or neither. So let's take a look at our do now. So for today's do now, we are given a function f of x and we want to find its symmetry. We're going to use an algebraic test to determine its symmetry. So I want you guys to pause the video, do the 3 tests, and see which of the 3, if any, the function is symmetric to. So for this one, I did the x-axis, the y-axis, and the origin test, and I only found that this function is symmetric to the y-axis. So what are we doing today? We are going to be looking at what are even and odd functions. We're going to test whether a function is even or odd. So the first thing we're going to be doing is a graphical test. If I have an even function, that means that the function is symmetric with respect to the y-axis. If a function is symmetric to the y-axis, what changes? We change our x, right? So I'm going to take what we did in the last video and apply it here. If a function is odd, that means that the function is going to be symmetric with respect to the origin. And if I have a function that's symmetric with respect to the origin, what changes? So we change the x and the y. Again, that's going to come in handy when I do the algebraic test. So let's look at a graphical example. So here in example number 1, determine whether each function's graph is even, odd, or neither, and explain. So if I look at the first one, first thing I want to determine is its symmetry. An absolute value function is always symmetric with respect to the y-axis. So we have, since I have a function that's symmetric with respect to the y-axis, that means that we have an even function. And the reason for that is because I have this piece here. So I'm not going to write anything else. For number 2, I'm going to determine its symmetry. Is this function somehow reflected through the x-axis, through the y-axis, or through the origin? This function has no symmetry. Since I have no symmetry, that means that it is neither even nor odd. The last one, what type of symmetry do you see? If I have a function that's symmetric with respect to the origin, that means that this function is odd. Again, what you're doing is you're looking at those ordered pairs to determine the symmetry. So if I have a graph, that's what I'm going to be looking at. I'm going to be looking at the ordered pairs, determining if it's symmetric with respect to the y-axis or the origin to determine if it's even or odd. The x-axis tells me nothing as far as if the function is even or odd. What about if I ask you to determine whether a function is even or odd, but this time algebraically? So if I have an even function, let's go back to the start, right? If I have an even function, that means that the function is symmetric with the y-axis. If it's symmetric with the y-axis, what changes? We said change the x. And that's exactly what we're going to do. So instead of our function being in terms of f of x, we're going to now change that input to a negative x. We're changing the x. If I end up at the same original function, so very similar to the algebraic test when we were doing symmetry, if we end up to the original, that means that function is going to be an even function. If I want to look for odd functions, what does odd mean? Odd functions are symmetric with respect to the origin. So what changes? We're going to be changing both the x and the y. So in this case, my f of x is going to become an f of a negative of x. And if it's an odd function, the function will be the opposite as the original. In simple, all signs are going to be negated. So we're not looking to see if it's exactly the same. This time, everything is just going to be opposite. So let's test this out. Let's look at our example. In example 2, we're going to determine whether the function is even, odd, or neither, but this time algebraically. So number 1 says, given the function f of x, a quadratic, we want to algebraically determine if the function is even or odd. If the function is even or odd, state whether the function is symmetric with respect to the y-axis or the origin. So first thing I'm going to do is I'm going to input f of negative x. So I'm going to change that x. So my original function was 2 times x squared minus 1. So this time my x is going to become a negative x. And I'm going to clean this up and see if I am able to get the same exact function that we started with. And I am. If I look at that piece, I see that it's exactly the same thing that we originally had, 2x squared minus 1, which means that this function, I was able to show same as original, this function is an even function. If it's an even function, what is it symmetric to? Symmetric to the y-axis. All right, number 2, we have been given our function, f of x, a cubic function. We want to determine algebraically whether this function is even or odd. Again, once we determine that, then we're going to determine whether it has symmetry. I am going to start off with the same test, f of negative x. I'm going to replace all of my x's with a negative x. I'm going to simplify it as much as I can. And this is what I get. Is this exactly the same as the original? No. Have every sign changed? No. Which means this is neither. Since it is neither, I cannot determine its symmetry. It may actually be symmetric with respect to the x-axis, but that's not what the question asked, so I am not going to do that extra work. Let's do 2 more. So for number 3, I have been given our function f of x. I want to algebraically determine whether it's even or odd, and if it's even or odd, I could state its symmetry. So let's start off by doing f of negative x. And I'm going to replace all of my x's. Now I am going to clean it up. All right, so now I am looking to see if this, what I got, its simplified version, is exactly the same as the original function. Clearly it is not. The next question I'm going to ask myself is this completely opposite of the original function? And in that case, yes, it is. What you're going to be focused on is the numerator. If you notice, the denominator is exactly the same. So it's kind of like pretend it's not there. But that numerator, is it completely opposite to the original numerator? Yes. So we have opposite here. Since it's opposite the original function, that means that this is an odd function. Since this function is odd, I could conclude that this function is symmetric to the origin. Last one. So for number 3, we have been given our function, f of x. Again, we're algebraically determining whether it's even or odd. And if I could find even or odd, then I'm going to find and determine its symmetry. So the test I am going to do is f of negative x. I'm inputting that negative x into my original function. I'm going to simplify, clean this up. Normally, when I have a negative in the denominator, we want to bring it to the top. That way the denominator is positive. We like positive denominators. And similar to the last problem, we do have the same denominator now, which is an x, which means all I'm going to be focused on is the top. is the numerator. And I'm going to ask myself, is the numerator completely opposite the original numerator? Originally, I had a positive 1. Now I have a negative 1. So that's opposite. Originally, I had a positive x squared, and now it's a negative x squared. Also opposite, which means that this is opposite the original. All those signs from the numerator changed, which tells me that we have an odd function. And if I have an odd function, it's symmetric with the origin. So for our algebraic test, what we are always doing is inputting f of negative x. If I come out with the original function, that means it's even. If I can see that what I got is completely opposite the original function, that means it's an odd function. So keep learning, keep growing, and I will see you in our next video.